Hello, everybody. I'm glad you could join me on our pavement materials and design journey. In our last lecture, we have learned the asphalt mix design. Today, let's learn about the structural design of flexible pavement. The flexible pavement design will take 2 lectures to cover the content, and this lecture mainly focuses on its first part. Since we have learned different pavement materials, the aggregate, the cement, the concrete mix design, the asphalt and asphalt mix design, it's time for us to combine them to design a pavement. Because of many variables and interactions which influence the result, it is appropriate to adopt a systematic method to design the pavement. The system for the design of pavement is shown in this flowchart. Although in a practical design procedure, some parts of this system may be omitted or combined with others, it is convenient to use this figure to demonstrate the relationships between the input variables and the analysis methods and the decision process which comprise pavement design. This lecture will focus on the project reliability, the construction and maintenance considerations, the environment, subgrade evaluation, and pavement materials. So the left circle, they are the input variables in the pavement design system. The next lecture will focus on the design traffic and structural design of flexible pavement. Once the design is completed, it could be implemented, and the feedback will be used to refine the design procedure. In the previous lecture, we have learned the structure of flexible and rigid pavement. For flexible pavement, it is composed of bearing surface, the base, subbase, and subgrade. While for rigid pavement, it is composed of cement concrete, subbase, and subgrade. The interface between the subbase and subgrade is the design subgrade level, the DSL. Normally, the pavement is a layered system, and the base and subbase may contain multiple bond or unbound layers. The bond layer is to mix the base or subbase material with binder, for example, the cement, to get better strength of that layer. The subgrade is the native material beneath the pavement. Here is the comparison between flexible and rigid pavement. Please pay more attention on the text in red color, as they are relatively more important characteristics of both pavements. We could rely on these characteristics to choose the type of pavement. Most highways in the world use flexible pavement due to its low completion cost and shorter time to repair. The aim of the pavement design is to select the most economical pavement thickness and composition, which will provide a satisfactory level of service for the anticipated traffic. In this pavement design system, the external factors are the project reliability, construction, and maintenance consideration, and environment. These factors affect the desired material performance. So let's go through them first. Then we will get to know the subgrade evaluation and pavement materials. An integral part of the pavement design process is an assessment of how well the outcome of the design, the constructed pavement will perform. Because of the lack of uncertainty, there are variations in the thickness, and the qualities of materials can vary from day to day. So the designer needs to allow for this uncertainty and variation in the performance prediction. An appropriate measure of the anticipated performance of the proposed pavement is project reliability. The project reliability is the probability that the pavement will outlast its design traffic before major rehabilitation. Normally, the road agency or designer chooses the designed project reliability. So typical project reliability levels are given in this table below. The project reliability is selected based on the class of the road. Either is freeway, highway, or other type of road. Here, the AADT means the annual average daily traffic. It is the total traffic volume on a highway or road for a year divided by 365 days. AADT is a useful and simple measurement of how busy a road is. Here in the table, the freeway you might design for reliability of 95%. If you choose that, it means 95 out of 100 constructed pavements of that design will outlast the design traffic. So there's only a 5% chance that the pavement will be distressed within the design period. And you can see the reliability levels that people use are often related to the importance of the road you prepare to take up a little more risk for lightly trafficked road compared with a heavily trafficked road, where the consequences of early distress result in significant road user cost to rehabilitate the pavement. We can see that the larger the AADT, the higher the project reliability from this table 2.1. The design procedure is based on the structural analysis of multi-layer pavement subject to normal traffic loading. The critical locations of the strands within a flexible pavement model and the idealized loading situation are shown in the in this figure 8.2. The pavement materials are considered to be homogeneous, elastic, and isotropic, except for unbound granular materials and subgrade, which are considered to be anisotropic. The response to load is calculated using linear elastic model, such as that contained in the computer program Circly. You will have more practice in your Lab 2 session. In the flexible pavement, the bond materials are made asphalt and cement, and they have the tensile strength. Here we can see that for flexible pavement, there are 3 critical locations: the tensile strength at the bottom of asphalt, the tensile strength at the bottom of cemented materials, and the compressive strength at the top of subgrade. Because that's where the cracking starts. So during design of the flexible pavement, we have to check these 3 locations and make sure the design value is acceptable. There are 3 damage models in these 3 critical locations: the asphalt fatigue, cemented material fatigue, and subgrade rotting, and the loss of surface shape. This formula is the fatigue relationship for cemented material, and it can be used to give an indication of fatigue life. The fatigue is the weakening of a material caused by cyclic loading that results in progressive and localized structural damage and the growth of cracks. This relationship generally has been found to be in accordance with observed performance. In the formula, the N is the allowable number of load repetitions. E is the modulus of cemented material in megapascal. The mu epsilon is the load-induced tensile strength at the base of cemented material. The RF is the reliability factor for cemented material fatigue, which can be referred from the table. We are having a design process allowing for the variability in performance between projects. So not all projects will perform the same. So we need to allow for that variability in our predictions of how long pavements will last. And we do that through the inclusion of reliability factors. When there's a higher project reliability requirement due to the class of the road, such as freeway, there's a smaller RF value, and correspondingly, the N value will be smaller as well. In other words, increasing project reliability will decrease allowable number of road repetitions. The predicted profiles of allowable load repetitions versus the microstrain mu epsilon for project reliability from 80% to 97.5% are shown in the figure below. In the above formula, the Young's modulus is provided as 2000 megapascal. So the only variable is the microstrain. We can see that for the same microstrain, the allowable number of load repetitions N increases with the decrease of the project reliability. So let's say for the same microstrain 100, so project reliability from the blue curve to the red curve gradually decrease. But then when we read from the vertical axis, the N actually increases. And you can see in this graph here, the significant effect the reliability factor can have on the predicted life for a given strain. So the choice of reliability level for the project has a significant effect on the life that you calculated. Similar as the cemented material fatigue model, here is the formula for the asphalt fatigue model. Most parameters are similar as the cemented material fatigue model, well, the only difference is the parameter, the VB here. So which is the percentage by volume of bitumen in asphalt. We learned this parameter in lecture 6, and it is the effective volume of bitumen excluding the absorbed binder. Also for the same E, VB, and microstrain, we can see from this figure that the allowable load repetitions, the N, increases with the decrease of the project reliability. So same conclusions can be found both for the cemented material fatigue model and asphalt fatigue model. After we discussed project reliability, next is the construction and maintenance considerations. The type of pavement structure could be affected by the construction and maintenance policies. Since construction also affects the property and performance of materials, considerations need to be taken during the construction include the compaction level, curing, concrete, or cemented materials, the type of equipment, and subsurface and surface drainage. For example, we need to make sure the pavement selected is compatible with the available equipment for construction. The environmental factors which significantly affect pavement performance are moisture and temperature. The modulus or strength of unbound materials and subgrains are heavily dependent on the moisture content of the materials. For expensive subgrade soils, the moisture changes in these materials can lead to volume change and affect the rate of the surface. There might have moisture infiltration the surface, or it might be coming through infiltrating the shoulders and then into the pavement. It could be coming from the water table underneath. So there are many factors that are affecting the operating moisture content and that need to be considered when the designer is selecting the subgrade strength to use in the design. Temperature environment also has a major influence on the performance of pavement. For asphalt surfaced pavement, the asphalt becomes stiff and relatively brittle at low temperatures when it is susceptible to fatigue cracking. But it is soft and viscoelastic at higher temperatures when it is susceptible to permanent deformation. Temperature may also affect the properties and performance of cemented layers and concrete. It could also have a significant effect on the rate of strength gain of these materials. And if high temperatures occur during construction, drain out will result impairing both the ultimate strength and fatigue characteristics of the materials.